the National Roundtable on the Environment and the Economy had a neat little statement where they looked at GHG. That was what the NRT, or National Roundtable on the Environment and the Economy, put value in, was mitigating the amount of greenhouse gas that we're spewing into the atmosphere. How much oil and gas are we burning? And what they said was that the question is not which technologies, this is in reference to renewable energy technologies. It's not which technologies to deploy, but how to deploy many or even all of the potential GHG reduction technologies at unprecedented levels of implementation. The phrase unprecedented levels of implementation, when you look at marine renewable energy, which was one of the big things that the NRT pointed to, does not really fit well with the precautionary approach. There's a little bit of an imbalance here. Yet, when you read the NRT documents, they are calling for 10 gigawatts of wave energy by 2050. That's 1/7 of all the renewable energy they want to see Canada have by the year 2050. That's a significant portion. And that 70 gigawatts of renewables is the second greatest factor, in their opinion, to the reduction of GHG. So if you want to put dollar signs on things and you choose to use GHG as a metric, wave energy plays a role. Everybody knows it plays a role. The problem is that when you read the NRT document, in the conclusions where they mention that number, that's about the only place where wave energy gets mentioned. There's no discussion of the technology that's going to do it in the document, because it's a bit of an enigma. Why does nobody know what a wave energy converter looks like? Well, waves are an extremely concentrated form of solar energy. It's a very academic thing to say. They're actually basically a battery for wind, is what I would say. If you're out in the Pacific and you have a long stretch of ocean and you have a coherent flow of wind over the surface, that builds up a gravity wave. You get a wall of water that literally builds up, and then it falls down and disperses and generates an oscillation that starts to perpetuate in a direction towards shore. That's called swell. Swell is not a wind wave that you see on a lake. This is about waves that are, the peak-to-peak time of arrival would be 12, 13, maybe even 19 seconds. These are big rollers that if you take a little boat out of Tofino and you go around the Broken Island group, you feel it. You're going up for a while and then you're going down for a while. And wave energy converters commercially are working off of that type of wave. So we're not looking at wind chop. The reason that wave energy converters are so different, and there's lots of physical phenomenon you can work with, and they're all really powerful. So when the ocean goes up and down, if you were to hold a cylinder and the ocean went up, more of that cylinder is getting displaced and the buoyant force goes up greatly. If you look at a wave underneath the surface of the water, there's a circulation pattern that's very strong. There's a tremendous amount of inertia behind it, and it extends almost, well, it goes down about whatever the wavelength is. So the waves are about, let's say, 15 seconds peak to peak. They're also about 150 meters peak to peak, and the circulation underneath them is going down in some places in deep water, around 150 meters. So you could work off of that circulation of water. You could put a device in, like a turbine even if you wanted to, something that was picking up on that rotation of the water, or you could work off of the oscillations of the free surface. And there's various classes of devices that do this. So Jessica showed you a picture of Pelamis. This is where, well, I guess I don't have to wave my hands today. The cylinders are basically pinned together, and they basically fall into the trough of the wave, and they bridge over the crest of a wave. And as they go up and down, they rotate relative to one another at the joint, and that mechanical energy is used to drive an energy system, compress air, push fluid, create electrons, take your pick, whatever energy commodity you want to. The ocean engineer's job is to maximize the amount of mechanical work at that crux. Overtopping devices are one where you're trying to create an artificial shoreline. The water comes up, breaks over the top, and falls down through a low-head turbine, usually generates electricity. This is Oyster. I wish it had a better name. I mean, Oyster seems ridiculous for something this size. But this is a terminating device. Basically, you array these things across the wavefront, and they're almost like an artificial breakwater. That's called the terminator. It's trying to kill the wave, take all the energy right out of it. The class that I work with sync wave systems is a point absorber. That'll be most of the focus today. Point absorbers are called this because if you were a bird and you flew over the top and you look down, the thing looks like a point. It's very small. Whereas the sea snake is a very long device that's aligned parallel to the direction of the wave flow. So how does this thing work? Well, if we put it in a simple schematic, here's the outer float, which I could, again, in a simple schematic, I could just redraw that as a great big fat cylinder sitting in the water, extremely buoyant. The spar would be hydrodynamically equivalent to a very slender cylinder also sitting in the water. And as a wave comes by, so if you consider the blue dot here kind of represents the wave motion. So if you were to watch that spot, as a wave comes by, that blue spot would go up and down. Because of the sizing of the cylinders, hydrodynamically they respond differently. They have a different resistance to the wave as it comes by. It's like an electrical circuit. And the float, what you would find is it actually moves, because it's so buoyant, it moves exactly like the wave. The spar, because it's slender and not so buoyant, it has a lag. And ideally, in a perfect world, it would have a 180-degree phase lag. It would be moving, once it got to steady state, it would be moving in the other direction. And if the spar was moving in the other direction from the float, if you look at the relative motion between the float and the spar, the two devices, you've just increased it. And when you've increased it, if you were to put a generator between them, you've just increased the amount of mechanical power being dissipated across that generator. And that's the idea with SyncWave, is that by taking that spar and not trying to put magic fingers on it and lock it in place, try and get it responding in a way where you're creating more relative motion, more power across the generator. Where will it be used? Again, we've looked at 2 integration studies in very different places. Does anybody watch The Deadliest Catch? St. George Island is one of the islands they drive around on those crab fishing boats. It's just north of St. Paul. It's in the Pirloff Island group. So we were actually, with SyncWave, commissioned by the community there to look at what would happen when we install a converter. Essentially, when you do those integration studies, what happens, and this is what gives you a complete picture of all the stuff that's necessary. You've got to do a wave resource assessment. We've made inroads on how to do that over the last 3 years. You've got to have a technology model which basically says, once I know what a significant wave height in a period is, once I know a sea state, how do I convert it into power? And then I got to basically multiply those things together and figure out what I'm producing. And if I want to know if the converter is sized right, I got to have an idea of what the load is from that community. And if it doesn't match up, then we go all the way back. Obviously, we're not going to change this, but we can change this. We can redesign it using some of the optimization tools and make adjustments. So it's a pretty comprehensive approach, but it's necessary in order to get the technology to commercialization stage. All right, in terms of people involved at SyncWave, some of the names that are there. Jim Adamson is the fellow who's basically in charge of the design of the ocean device. I'm down here, and basically I liaise between SyncWave and the IceFic Institute. The West Coast Wave Collaboration, which is putting a wave buoy in the water, I'll talk about this disaster in a second, and doing wave resource assessment on West Vancouver Island involves a lot of people. In terms of people at IceFic, long list. We've got a really committed group, and I won't go into everybody's name, but I wanted to make sure I threw their pictures up there. At IceFic, our main thing in terms of our cooperation with SyncWave is to help out on the wave resource assessment. This is a huge task when you're dealing with a technology developer who's not only developing a technology, but they also got to quantify what the resource is and where it is, and that's our role there. And then we work with some of the advanced control systems on the swells unit as well. When will the wave energy converter be in use? Well, the ocean demonstration device, just a little figure of kind of what it looks like here, is aiming for completion, that project in 2012. And if you have more questions on that, actually the guy to talk to is Klaus. We are doing some small scale testing right now, and then next year we're hoping to lead into another 1 to 15 scale model, which is very similar to Charlotte. This one will be called Beverly, that's my mom's name, and we'll be looking at more involved controllers on swells and trying to implement some of the ideas that we've arrived at via numerical simulation or numerical analysis. So that would be with SyncWave Energy. One of the questions at the beginning talked about, what are the advantages? What's the state? Where are we at? How much for this? How much for that? How does it compare? Hopefully I've given you a glimpse of all the work that we have to put into getting towards the answers to those questions. And while we don't have answers to those questions now, I can tell you that there are advantages, and I can tell you that there are communities that need this. It's not your community, but there are communities that do. It is coming. And I think through the passion in our group, we've gone from drawings that, really, while functional and while guiding our optimization study, this is second year engineering school, this is getting more advanced. This is proof of concept. This is taking data. This is validating ideas. This is getting more advanced. This is looking at wide tracts of ocean and figuring out what a resource is on an ongoing basis and providing that data to all who want it. And this is getting more advanced still. So there's a passion in our group, there's a passion in SyncWave, and we've prepared ourselves, I think, to capitalize on an opportunity that is coming. So hopefully I've given you a taste of what wave energy conversion is all about. And if somebody asks you what a wave energy converter looks like now, hopefully maybe some of you can put up your hand. So thanks for your time.